All right, let's do another example. In this one, you'll learn some math for this one. An airplane flies from San Francisco to New York about 4,800 kilometers at a speed of 300 meters per second. How much time does the trip take as measured by an observer on the ground and an observer in the plane? Now, before you even do anything, I mean, come on, the plane is going 300 meters per second. So that's 3 times 10 to the second meters per second. But the speed of light is 3 times 10 to the 8th meters per second. So do you expect much of a difference here? Certainly not, because 300 meters per second is nothing compared to the speed of light. So maybe this is a waste of time even doing this. Well, it's not, because you're going to learn a math trick. All right? So, okay. So let's just go through the method like I talked about last time. If you follow this method, you'll most likely get the problem right. So it's really worthwhile. Okay, number one, what are the reference frames? Well, you know, the Earth and the plane. So Earth and the plane. Number two, what are the events? Well, the takeoff and the landing. So takeoff and landing. Okay, now, again, these are the crucial questions. If you answer these questions incorrectly, you'll get the problem wrong. So you have to be able to figure out who measures proper time and who measures dilated time. So remember, proper time, the person who measures proper time is at the same location at each event. So who's at the same location in each event? The plane, right? Or the person in the plane, you know. They're at the takeoff, and then they're at the landing. Okay, so proper time, I mean, if you're going to be technical, the proper time is measured by an observer in the airplane, right? Because the observer in the airplane is at the same location relative to the airplane at the takeoff and at the landing. So proper time, an observer in airplane. Just plane. All right, now, who sees the events at different locations? The person on the Earth. So dilated time, observer on Earth. Okay, so now you got to get to work, right? Okay, so you notice you also have to calculate the gamma. All right, so delta T is the dilated time. That's what we would measure on Earth, right? So delta T, I guess I put whatever. So delta T, you know, distance equals rate times time, right? So delta T is just the distance, 4,800 times 10 to the third meters, over the speed, 300 meters per second. And that equals 1.6 times 10 to the fourth seconds. All right, so, you know, whoopee. That's what we would calculate here on Earth. All right, 6 gamma. So gamma is 1 minus beta squared, negative 1/2 power. So that equals 1 minus, so it's 300 meters per second all over 3 times 10 to the 8th meters per second squared negative 1/2. Now, please pause the video, use your calculator, and figure this out. Okay, so if you have a normal everyday calculator, which I assume you do, you either got an error or you got 1. Now you know it's not 1, right? Because it's 1 minus something. So it's not 1. So what's the problem? The problem is that your calculator doesn't have enough digits. So that's why we have to learn a math trick. All right, so let's go back to high school algebra. Okay, a long time ago when you took algebra, maybe here at BYU when you took 110, you learned something called the binomial theorem. So this is a constant. So constant minus x to the n power equals all this. All right, great. Now let me write gamma again. So we're going to use that to simplify this. So here we have a 1 minus something. So we want to put a equal to 1. So now we have 1 minus x to the n power. And it's equal to all that stuff, right? Everywhere you see an a, you put in a 1. Okay, now, man. Okay, this is some crazy projector problem or something. This is supposed to be very much less than. That box, I mean, it's on my computer, very much less than. So it's supposed to say, for x, very much less than 1. Okay? So look, we know that beta, remember, is 3 times 10 to the second over 3 times 10 to the 8th, which is super small, right? If you square a super small number, you get a super, super, super small number. So all I'm saying is this x here, you know, the x is the beta squared. This beta squared is tons less than 1. So we're going to use this approximation. All right, so if x is much, much less than 1, basically what it means is that, you know, what's super, super small number squared? Incredibly small, or cubed, or to the 4th. So for this condition, x much, much less than 1, these terms here are so small, you can just ignore them. So we do. So now we just have this. 1 minus x to the n equals 1 minus nx. All right. Now, what we want, though, we want n, you know, the exponent, to be minus a half. So just do it. So you just put in minus a half for n. And then you get 1 minus x minus 1/2 is approximately equal to 1 plus, right? If this is minus a half, minus minus is plus. So you get plus x over 2. So that's the math trick. So the math trick is 1 minus x to the n equals, well, sorry, to the minus 1/2. 1 minus x to minus 1/2 equals 1 plus x over 2. That's only true if x is tons less than 1. Now, you don't want to memorize it, but you ought to know how to use it, okay? Okay, so that's what we're going to use. All right, so let's go back. So what we have then is, oops, sorry. So we have gamma is 1 minus beta squared, negative 1/2. That's the same thing as 1 plus beta squared over 2, right? Because the x is the beta squared. So you plug that in, and I promise you, this is what you're going to get. You're going to get 1 plus 0.5 times 10 to the minus 12. That's incredibly, I mean, come on. What's 0.5 times 10 minus 12? It's incredibly small, right? But you can see it's greater than 1, because gamma always has to be greater than 1. And so it is, okay? So then what we want to do is find our proper time, right? So we calculated gamma. Now we want to calculate proper time. All right, so proper time. Okay, so remember, here's the equation. Delta t equals gamma delta tau, right? Dilated time equals gamma times proper time. So proper time equals dilated time divided by gamma. So it's that, 1.6 times 10 to the 4th seconds all over this. And all I can say is, I mean, it's just a little bit less than 1.6 times 10 to the 4th seconds. Okay, so there you go. All right, so did it make much of an effect? Of course not, because the plane is going much too slowly. But this is something that you want to understand, because you use it when the object is going slowly compared to the speed of light. So there you go. Okay, so we spent a long time talking about time dilation, how time is relative. Well, time isn't the only thing that's relative. Space or distance is also relative. And I'm not going to go into as much gory detail as we did with time. I'm just going to give you the result. Oops, sorry. So here's the result. So we have a contracted length and a proper length. And the equation is that the contracted length is the proper length divided by gamma. And it's easy to remember because, you know, contracted means smaller, right? Gamma is always greater than 1, so this has to be less than the proper length. Okay. And here's a cool graph. And so you can see, let's say I have a meter stick. So I have a meter stick and I'm running relative to you. So according to me, the meter stick is a meter long. But according to you, since I'm running relative to you, you're going to see the meter stick smaller. But again, it really depends on the speed, right? So let's say we're down here where we are with our fastest missiles, our fastest anything on the Earth, and the meter stick is going to be a meter stick, right? I'm going to say a meter, you're going to say a meter. But look, if I'm going at half of the speed of light relative to you, I still say it's a meter long, but what are you going to measure? You're going to measure 0.86 or something like that. If I'm going at 90% of the speed of the light relative to you, you're going to measure the meter stick to be like 0.4 something meters. If I'm going nearly the speed of light, you're going to measure it to be super tiny, right? So that's called length contraction. Length contraction. Here's a good one. The length of objects appear to be contracted or shortened when they move by us. So see, this alien, he's carrying a meter stick. And according to him, the meter stick is a meter long. But what do we say? We say, my gosh, it's shorter than a meter. All right? Because distance is relative, just like time, just like space. I mean, just like size, sorry. All right, now again, just like with time, the crucial point is to figure out what's the proper length and what's the contracted length. So you got to understand this. So the proper length, which is this, right? Without the thing there, without the prime. So the proper length in a particular reference frame is a length measured on an object at rest in that reference frame. So, you know, once again, if I'm running, but I'm holding this thing, this meter stick is at rest relative to me. So I would measure the proper length, right? And the proper length would be a meter. Okay, so proper length, you're measuring the length of something when the object is at rest relative to you. That's the crucial point. At rest, okay? So the shorter, or the contracted length, L prime, is the length between the same 2 points on the object. So, you know, here and here. As measured in a second reference frame that has a speed relative to the first. So according to me, you know, I'm saying I'm at rest, right? And according to me, you're moving that way. So you would measure the contracted or the shortened length. Okay, so here's a question for you. You watch a spaceship fly by at 0.75 c. Compared to an astronaut in the spaceship, you measure the spaceship as being shorter, as being longer, or the same. So pause your video and figure it out, please. All right, so you are watching the spaceship fly by. So the object is not at rest in your reference frame, correct? So you're measuring the contracted length. So the answer is this. So you would measure the spaceship as being shorter. And again, that's just what shows in this picture, right? You know, you measure the spaceship is moving past you. You measure the meter stick to be less than a meter. Oops. Okay, so let's do an example problem with this. A crew member on a spaceship traveling at 0.99 c relative to Earth measures the length of the ship to be 400 meters. What length do observers measure on Earth? Okay, let's just go through the procedure. 1, what are the reference frames? The spaceship and the Earth. Spaceship and Earth. Number 2, who measures the proper length? Well, who's at rest relative to the spaceship? The crew member, right? So the crew member. So proper length is the crew member. Okay. All right, what is the proper length? Well, 400 meters, right? That's what it, right? That's what it says. That guy on the spaceship measures the length to be 400 meters. So proper length, lowercase l, is 400 meters. Who measures the contracted length? Person on Earth, right? So contracted length is measured by somebody on Earth. All right, okay. So calculate it. Well, what's the formula? The formula is L prime equals L over gamma. So like I keep saying, whenever you do these relativity problems, you got to always, generally speaking, you have to find gamma. So gamma, 1 minus beta squared, negative 1/2. Okay, so 1 minus 0.99 squared, negative 1/2. Don't forget you got to square it, right? And that comes out to be 7.089. So therefore, the contracted length, it's a L, is 400 meters divided by gamma, and that's 56.4. Okay, so this is true. This is not just imaginary, you know? Again, the crew member says 400 meters, the guy or whatever, 400 meters long. But when we see it traveling past us at this incredibly high speed, and we measure the length, we measure 56.4 meters. Because length is relative. Okay? All right. Okay, let's do another one. I'm doing a lot because you're going to have to do these on the test and on the homework. So let's just get used to doing them. An astronaut in a rocket passes a meter stick moving parallel to its dimension, to its long dimension. Oh yeah, I forgot to say something. This length contraction only occurs in the direction of motion. Okay? So in other words, if I'm running like this, you're going to say the meter stick is shorter, but you're not going to say anything about the width, right? The width isn't changed. Okay, so an astronaut in a rocket passes the meter stick moving parallel to its long dimension. The astronaut measures the meter stick to be 0.8 meters. So how fast is the rocket moving? So this is kind of a different problem, right? Usually we say, the rocket is moving at such and such a speed. How long does the meter stick appear to be? Now it's kind of different, right? Now we're saying the meter stick appears to be 0.8 meters long, so how fast is the rocket going? So that's a little different, but it's okay. But, okay, what are the two reference frames? Spaceship and Earth. Okay, who measures the proper length? Who measures the proper length? Well, it sounds kind of funny saying who. Who measures the proper length? The meter stick, right? Or the guy on the meter stick. There's not a guy, but who cares? Right? The meter stick measures the proper length. Meter stick. Proper length. Proper length meter stick, right? And what is the proper length? Well, what's a meter stick? It's a meter. So, okay, so meter stick L, which is 1 meter. 3, I already said that, sorry. 4, who measures the contracted length? Well, remember, the meter stick is moving relative to the crew member, or the astronaut, right? So the astronaut measures the contracted length, L prime. And what is that? It's 0.8 meters. Okay, so guess what? Calculate gamma. So let's do that. Okay, so L prime equals small l over gamma. Therefore, gamma equals L over L prime. So that's 1 meter over 0.8 meters, and that's 1.25 meters. Wait a second. No, 1.25, yeah. Okay? All right, so now we know gamma, but it says that we want to find the speed. That just means calculate beta. So again, gamma equals 1 minus beta squared, negative 1/2 power. So if you, so square it to the negative 1, right? So in other words, raise this thing here to negative 2 power, raise this thing here to negative 2 power, so 2, sorry. So you have gamma, negative 2, and that cancels, right? Equals 1 minus beta squared. Therefore, beta squared equals 1 minus gamma, negative 2. Therefore, beta equals 1 minus gamma, negative 2 to the 1/2 power. And you plug it in, I promise you, you get 0.6. So beta is 0.6. That means that the velocity is 0.6 c. Let's see how well that agrees with our chart, our graph. All right, so 0.6, 0.8. Woohoo! Perfect, right? Perfect. Okay. So you need to be able to do these problems, you know, if they ask for the speed of the object or if they ask for the contracted length or time or whatnot. You should be able to do both of them. All right, now we're going to watch a video. And it's a really awesome video. So let's see. And let's see, 20.55. It's not very long. All right, let's go. It's a very old video, so you don't expect to see modern graphics or anything like that. All right.
A number of years ago in Germany, a man gave to the world a new concept. It shook the scientific world from top to bottom, changed the course of human history, and gave us the atomic age. The man, Albert Einstein. The concept, relativity. That strange, fantastic relationship between time, distance, and mass. Now, an important part of that concept can be expressed in a simple equation. E equals mc squared. Energy equals mass times the speed of light squared. The equivalence of mass and energy. The basic formula that unlocked the secrets of the atom. But equally, if not more important, is that relationship between time and space. Now, we can't speak of the equivalence of time and space. They're not exactly equal. But we can say that they are relative, or they are all bound up together. Just obtuse theory, you say? Well, maybe so. But every day there is new concrete evidence to prove it true. When Dr. E.O. Lawrence and his associates at the University of California designed the 184-inch cyclotron, they didn't laugh at this theory. They accepted it as true, and it's a good thing they did. In the cyclotron, tiny particles are accelerated in magnetic and electrical fields until they approach the speed of light. This rotary condenser at the side of the cyclotron compensates for the increased mass of the particles which occurred exactly as Einstein had predicted it would. Let's suppose that at some day in the Buck Rogers future, you decide to take a trip to a planet satellite of the star Sirius. As long as we're supposing, let's say that your atom-powered rocket ship is capable of traveling at 99 and 99,999,999 100 millionths% of the speed of light. Now, of course, this is very close to 186,284 miles a second. In view of the fact that Sirius is 9 light years from the Earth, it would take just a little over 18 years to make the round trip. Naturally, you'd plan to take a large supply of food, but all you'd need would be a sack lunch. Traveling at this speed, not only would your watch slow down by a factor of 70,000, but your heart, respiration, digestion, appetite, all would slow down in the same ratio. You could leave the Earth some morning right after breakfast. By the time you got to Sirius, you'd be ready for a sandwich. And when you got back to the Earth, you'd be just hungry enough for a good dinner. But then would come the surprise. You'd find that while you were only 1 day older physically, your children would all be grown up and through college, and all your friends would be 18 years older than when you left them just 12 hours ago by your watch. A concept such as this is almost impossible for the human mind to grasp. It's so far beyond our normal experience. But maybe this will help. First of all, listen to my heart. Now, let me start the clock so that you can become accustomed to the rhythm of its beat. The yardstick. It looks normal, doesn't it? But if we could accelerate this room and everything in it to the speed of light, 186,284 miles a second, time would stand still. My heart would stop beating and I wouldn't die. The clock would cease to run. And everything would squeeze into a line, infinitely thin. Now, we can't speed the room up to the speed of light, of course. But with the magic of some very special photography, we can show you exactly what would happen if we could speed up the room to 90% of the speed of light, 167,000 miles per second. Are you ready? All right. There's our speedometer. And we're going to travel in that direction. You notice what's happening?
My voice has changed. Look at the clock. Listen to my heart.
This time, we're going to accelerate vertically instead of horizontally.
Now the yardstick is 18 inches long, approximately when we hold it vertically. Then it comes back to 36 inches.
When we bring it to the horizontal. When the room was accelerated, everything seemed normal to me. My voice sounded the same. The rhythm of the clock remained constant. The yardstick seemed the same in both directions. That's because I was accelerated along with the room. But you, as a stationary observer, were aware of the changes. Now, of course, the visual effects which you noticed were achieved in this case by the use of a Panavision lens, a variable aspect ratio lens. But the effect was exactly the same as if the room had actually been accelerated to 90% of the speed of light. These are called relativistic effects. They are based on mathematical formulas that are as common in the workaday world of the nuclear physicist as 2 times 2 equals 4 is in our world. Fantastic as they may seem, these are the formulas that gave...
All right, let's quit.